In today's video, we'll be looking at how to evaluate overall heat transfer coefficient. So now we know that when we say heat transfer coefficient, what comes in mind is the heat of convection, right? Convection, right? Because from the heat of convection equation, using the Newton's law of cooling, HAT minus T infinity. This H here is called heat transfer coefficient. Now, but this one is overall. So what it means is that we have a lot of convection heat transfer going on. So we are going to sum all their coefficients and then we'll call it the overall one. So let's say we have a metal slab, right? And then a hot fluid is being made to flow around the metal slab, right? So we have a hot fluid here, which is being exposed to the one side of the metal slab. Now heat will be transferred from the hot fluid to the surface of the metal slab, and then heat will be transferred from the metal slab to the other surface, right? So now when you have another cold fluid here, right, then now here it become hot, and then it also loses heat from this hot surface here to the cold stream. Right? So let's call this the heat transfer, and then this is our hot fluid, and this is our cold fluid. Let's call our T at the surface here T1, and then here to be T2. And then our heat transfer coefficient, because we know the heat transfer from the hot fluid to the surface will be by convection, right? So we should have heat transfer coefficient here. So let's call it HC, I don't know how to call it. Let's say HF, yes, to represent heat transfer of the hot fluid. And let's call this part HCF, heat transfer by the cold fluid. Now, and then let's call the temperature of the hot stream to be THF, hot fluid, and then TCF as a cold fluid. Right. So now the heat transfer from this hot fluid to the metal surface here is by convection, right? So I kill. Now let me establish this. So like the way we did for the composite wall, the heat being transferred from the hot fluid to the surface here will be the same heat that will be transferred from this point to this point. And that will be the same heat that will be transferred from this point to this point. When I'm talking about heat here, I'm not talking about the same temperature. They are saying heat, right? So now our heat here Q. So let's just if you still don't get it, so take it as electrical pathway, right? And then they are in series. Now if they are in series, it means that so we have resistance, resistance, resistance here. They are in series. When they are in series, we know that the same current will be flowing through. And then from our previous video, we said that the current is just like our heat transfer. And this our resistance is our thermal resistance. And our temperature difference causing, or the potential difference causing the driving of the heat, or the driving of the current in this case is our temperature difference. Right? We realize that the current passing through this resistor will be the same current passing through this, the same current passing through this. So the same idea here. The heat transfer passing through here will be the same passing here, will be the same passing through here. Now for the first part, because it will be the same, I don't want to differentiate them. So now for the first part, which is by convection, they are the same though, but I'm writing convection so that we understand that it's the first part. So from this point to this point, it's going to be HF, right? Because you know for heat of conduction, so heat for convection is supposed to be HA changing T. So HF multiplying the area of the surface, multiplying THF here. But now this will be at a higher temperature than this, minus T1. Now from this point to this point, the heat transferred by conduction, right? So heat of conduction will now be thermal conductivity of the wall. So K multiplying our A, the area will still be the same, multiplying T1, because now this will be at higher temperature than this, minus T2 all over change in X to the thickness of it, right? And then our heat from this surface to the cold fluid will also be by convection. So HCF multiplying A multiplying T2 minus TCF. But this will be at a higher temperature than this. Yes. So now we've already established that resistance by convection, or we even say that heat transfer can be written as change in temperature over resistance. Right. Right. And then we even say that from our previous video. So the same thing applies. Okay, let me establish that again. So now for the first part, this the resistance will be 1 over HFE. Right. For this part, so let me call this part A, part B, and then part C. So the resistance in A will be this. The resistance in B, which is from this, because it's by conduction, going to be changing X over K. And then the resistance in C, which is from this, is also by convection. So 1 over HCF times A. Right. So our Q convection for the first one, which is this, will now be THF minus T1 all over RE. And then the resistance in conduction, which is this, will now be T1 minus T2 all over this thermal resistance RB. And then the other convection, which is this, will now be T2 minus TCF all over RC. So now we can make this the subject. So if this is equation 1, equation 2, equation 3, we can see that our THF minus T1 will be equal to Q. Now the Q's are all the same, so we can just clean them and see Q throughout, right? So the Q's are the same. So you can just see that they are both Q's. So from this, from the equation 1, THF minus T1 will be equal to QRE. From equation 2, T1 minus T2 will be equal to QRB. And then from equation 3, T2 minus TCF will be equal to QRC. So now let's combine them. So let's add equation 3 plus equation 4 plus equation 5 to get the overall temperature difference. So THF minus T1 plus T1 minus T2 plus T2 minus TCF to be equal to, so we are going to add the equal signs to. So QRE plus QRB plus QRC. Now realize that this is negative, this is positive, they cancel out. The same thing applies here. Now we get THF minus TCF, which is actually what we want, because we want to see the overall temperature difference. So the actual temperature difference is from the hot fluid to the cold fluid. So that is the net heat transfer. And this should be equal to, you can factorize the Q out and say you're going to get RA plus RB plus RC. So our Q now becomes THF minus TCF all over RA plus RB plus RC. So now let's put in our RA, RB, and RC. So we could have done that straight away, because from our previous video we said that our Q will now be equal to overall temperature difference all over summation of our resistances. And these are resistances, right? And overall will be from THF to TCF. So we could have been writing this straight away. So THF minus TCF all over our RA is 1 over HHFA plus our RB is this change in X over KA, and then our RC is this 1 over HCF times A. Realize that there is area in all of them, so you can factor the area out. We are doing this because we want to get the overall heat transfer coefficient. So THF minus TCF all over, can bring our 1 over area out. Then we get 1 over HHF plus 1 over change in X over K plus 1 over HCF. Now this is 1 over area, so it can come up, and then we can see that our K will be equal to A multiplying THF minus TCF all over 1 over HHF plus change in X over K plus 1 over HCF. So now we have that, and then so we are almost done in finding overall heat transfer coefficient. Okay, so now we know that our K is equal to A multiplying THF minus TCF all over 1 over HHF plus change in X over K plus 1 over HCF. So now from this, the overall temperature difference here is as a result of heat transfer by convection, right? So when you want to fit this into a heat transfer by convection equation, this our Q is our Q, our A is our A here, our change in temperature here is now our change in temperature here. So we are left with our H, right? So now our H here will be equal to, sorry, let me write it well. We know that our heat transfer by convection is equal to H multiplying A T minus T infinite, right? So now this are Q, right? This are change in temperature, and now this are area, right? So I left it at H. Now 1 over H becomes 1 over HHF plus change in X, change in X. So is it 1 over H? Oh, I'm making mistakes. So now our H here becomes 1 all over 1 over HHF plus change in X over K plus 1 over HCF. Now this H is what we are going to call as overall heat transfer coefficient, U. Now this becomes our equation for overall heat transfer coefficient. Now this is not fixed for every problem, but then the idea is always the same, that overall heat transfer coefficient is always equal to 1 over the heat transfer by convection, by conduction, and then by convection. So in the case in which we had like 5 metal slabs dipped in a hot fluid and a cold fluid, our heat transfer coefficient will just be 1 all over, so the hot, all 1 over the hot heat transfer coefficient of the hot fluid plus, so change in XA over KA plus change in XB over KB, like for the different metal slabs, and then finally plus our cold medium. So that's it. So now we use this only when the starting and then the ending point of the heat transfer are fluids. So if they are fluids, then we can talk of the heat transfer coefficient. But in a case where they are just metal slabs alone, just like what you did in our previous video. So you have a metal slab here and then here, and there is no fluid, then we can't talk of overall heat transfer coefficient because this is attributed to heat transfer by convection, not by conduction. However, we have resistance by conduction here because the conduction is now in between the heat transfer by convection.